can start now.
Yes, sure. So in this section, we'll be trying to do non-standard FEs, which are from naturals to naturals, and we'll be using number theoretical arguments to solve them, and trying to use the standard ideas to solve none. So is the first problem visible?
Yes.
Yeah, so you can take 5 minutes to solve this. Like just, okay, first of all, like in an FE, first try to guess the solution. So what solution do you like first guess F should actually be? F of x is equal to x. Can you repeat? F of x is equal to x. Yes, so f of x is equal to x is a valid solution. Are there any more solutions? Hopefully no. So we'll try to prove that f of x is equal to x is a solution. So first of all, the problem says that for all positive integers a and b, we have that f of a plus b divides a squared plus f of a. We can take like 5 minutes to think about this. That to prove that f of x is equal to x is the only solution. Try to use the standard ideas that you do while solving in FE. Even though there is a divisibility and no equality, try to just use standard ideas to get it more. Yes, sir. Any ideas?
I got f of p is an odd multiple of p.
So you got that f of p is prime, right?
No, any odd multiple of p.
Okay, it's odd multiple of p. Okay, how?
Plug in a equal to b equal to p. Oh wait, I read the question wrong. I read it a plus b divides that thing. Never mind.
Oh, any other ideas?
Can we let f of sorry a is equal to b?
Yes. So we have two ideas. First, we will do f of a equal to, like we'll do b equal to a. So we have that f of a plus a divides a squared plus f of a squared. Now in this, like in the chat, we have that someone is said that f of 1 is equal to 1. This is just because just put a equal to 1 in this. You will have that f of 1 plus 1 divides 1 plus f of 1 squared. Right? One second. So you have that f of 1 plus 1 divides 1 plus f of 1 squared minus f of 1 squared minus f of 1. This is just because f of 1 plus 1 also divides this thing, and thus it must divide their difference. Yes. Someone also said that this actually implies f of a plus a divides twice of a squared. So I'll just do it for f of 1 and then you can generalize for a squared. This gives that f of 1 plus 1 divides 1 minus f of 1, or equivalently f of 1 plus 1 divides f of 1 minus 1. This clearly implies that f of 1 has to be 1. And for this proof, we'll just do the exact same argument. That is, we first have that f of a plus a divides a squared plus f of a squared minus f of a times f of a plus a. This is again because f of a plus a divides this thing and thus must divide its difference. Thus f of a plus a actually divides a squared minus f of a times. Now we can write that f of a plus a divides a squared minus f of a times a plus a times f of a plus a. Again, just because f of a plus a also divides this and thus must divide its sum. Thus simplifying, we get that f of a plus a divides twice of a squared. Now, what is a good choice of a?
Fine.
Sorry?
Putting a is a prime number.
Yes. So we have that f of p plus p, where p is a prime, divides twice of p squared. And twice of p squared has nice divisors. So we have that f of p plus p can only possibly be 1, 2, p, 2p, p squared, or 2p squared. But note that as f draw was from positive integers to positive integers, thus this number is actually strictly greater than p. Thus we cannot have that f of p plus p to be actually equal to 1 to 1. So f of p plus p can be either 2p, p squared, or 2p. And we want f of p plus p to be 2p, right? Just because we want to prove f of x is equal to x is the only solution. So in the other cases, we have that f of p is either p squared minus p, or 2p squared minus p, or p. So what if f is actually p squared minus p? What do we do then?
We put a is equal
Put it
to
back
p,
into the equation.
p is equal to p in our initial equation.
Yes, we put p equal to p. Hello? Can you repeat what you said?
We can put this in our initial.
Original equation. So yes, what value of a and b should we choose? B equal to p and a equal to?
We can choose b equal to a equal to 1. Then
B
show
equal
that f. Then show that fp equal to p square minus p is not possible. That will be 0.
You want to put B equal to 1 and A equal to P.
Other way around.
Other way around, okay, sure. I'll do other way around. Oh, it just happened.
You press the control key.
So other way around, we want to put B equal to P and A equal to 1. So let's see what happens. What is the original FE? We have this thing and we put A to be 1. We have that 1 plus P divides 1 plus P squared minus P. Yeah, this is a contradiction. And similarly, we get a contradiction for 2P squared minus P. Is this clear to everyone?
Yes.
Yes. So we must have that
Yes.
F. Yes, so we must have that F of primes is prime.
P equal to 2 works though. We'll have to check that.
Yeah, forget about this for a large enough primes, large primes.
Or you can
Yeah,
just
for a lot of values, F of P is equal to P. That is good enough. The large prime. Even though in this large it is greater than equal to, but anyways. Now what should we do? We have for a lot of values, F of P is equal to P, which is what we want to prove. And we just want to do it for all values. How do we finish?
We
we
test
can-
out p as a non-prime.
1 second. Yes. I'll just write what information we have that we first of all have F of A plus B divides P squared plus F of A times F of P. We have F of P is equal to P for large enough primes and F of 1 is equal to P. Yes. And now what are you saying?
We just try out for non-prime values, opposite values. So now if we assume p is not prime, we get an a plus b
P is not
divides-
prime.
Yeah. No.
And-
We assume that a and b are both not primes.
Okay.
So
if you take like A as a prime and just take B, you
Yes,
get
yes.
that P plus B divides B times B minus F of B.
P times P plus F of B, right?
No, B times B minus F of B. Oh, after reducing, I'm saying. You can go.
Right. Yes, you have that P plus B divides F of B, B minus F of B, yes.
F of a whole multiplied by a B also.
We can remove that, right? P plus B and B
Yeah.
are co-prime.
Yeah. Just now the right P large enough such that P plus B is greater than that thing, and which means like
Yes.
B minus F of B should be 0.
This must be 0. Right.
How do you get that F of B is 0?
Yes, and no, we get that B minus F of B is equal to 0.
Sorry, yes. How did you get that is 0?
Just because P can be arbitrarily large. So we have an arbitrarily large number dividing a finite number B minus F of B. Fix B for a moment. So we have P plus B, which can be arbitrarily large, dividing a finite number. So that finite number must be 0.
Okay.
Does everybody follow this step? This step. How do we get from P plus B divides P times P plus F of B to P plus B divides B minus F of B?
Yes.
Yes, sure. So yes, we have that F of B is equal to B for all B. And this is what we wanted to do. Is the proof clear?
Yeah.
Perfect.
Also, is this 2016 N6?
2016 N6, I don't think so. I mean, this was APMO 2019 one.
Okay. Because in that also, like, you got same cases as far as I remember, so I confused.
Yeah, like I took it. I did this problem from my right away. That was APM P1. But anyways,
Yeah.
yeah. So next problem. Right. So is the problem visible, right? Oh, yes. So let n be the set of positive integers. A subset A of n is sum free if whenever x and y, not necessarily distinct members of A, they sum x plus y does not belong to. Determine all surjective functions f from n to n, such that for each sum free set, the image f of small a, where small a is in capital A, is also sum. Okay, a function is surjective if for every positive integer n, you have there exists an m such that f of m is equal to n. So first of all, what are the guesses?
f of x is equal to x.
Yes. Does any other function work? Like this cx works.
That won't be surjective.
Yes, exactly. So we hope that f of x is equal to x is the only solution. Now we want to prove it. Now take 5 minutes to think about this. Any ideas? Any ideas? No ideas? Okay. First of all, sum free sets are not that good, right? If a set is not sum free, that gives more information. Like if you have a 3-element set XYZ, which is not sum free. If you have 3-element set XYZ, which is not sum free, you actually have some condition in Z in terms of X and Y. So not sum free sets actually give more information than sum free sets, like small sets. So like we'll restate the problem to non-sum free sets. That is just because for the problem says that for each sum free set, this implies that its image is also sum free. So we'll just negate it. That is for a non-sum free image set. That is for the set f of small a, which small a is in capital A. If this set is not sum free, second. Yeah, I'll just give you time 1 second. Not sum free. This implies that the original set was not sum free, I guess. Just because if the original set were sum free, if the original set were sum free, then by our problem statement, its image must be also sum free. But you assumed its image is not sum free. As the function is surjective, we can actually create this set to be good enough. So yeah, we can. What was your idea?
Okay, so like if we take the set 1, 2, k for any k that is greater than 3, then f of 1 plus f of 2 cannot be equal to f of k for any k that is greater than or equal to 4. But f of 1 plus f of 2 has to be f of something. So that something should be 3. So f of 3 should be equal to f of 1 plus f of 2.
Okay, so you're saying that this implies the set 1, 2k is sum free, not sum free, right?
It is sum free for any k that is greater than or equal to 4.
Yes. So 1 second. But note that this is already not sum free, right? 2 is equal to 1 plus 1. And the original set of x and y not necessarily distinct.
Oh, right.
But your idea is very nice. You just do it for 3. Okay. So set 1, 3, and k is not sum free. Thus k must be either 2 times 1, 2 times 3, 1 plus 3, or 3 minus 1, which is 2. So k can be either 2, 6, or 4. Right?
Okay.
Good. This idea is very nice. We will be using this idea quite frequently. So now this, like, we want that k should be 4, right? So what if k is 2? That is, what if you have f of 2 is equal to f of 1 plus f of 3?
Then what if we take 2, 3, k?
So you mean to say this, right? Is equal to some k. Then the set, then k can be either 2 times, just because the set 2, 3, k is not sum free, you must have that k is either 2 times 2, 2 times 3, 3 minus 1, or 3 plus 2. Yeah. So k, just because of this assumption, we have that k is clearly not 1. Like just because we were working positive integers to positive integers, it's strictly greater than f of 1. So if this were f of 1, that would be a clear contradiction. So we must have that this should not hold. Now, what if this is f of 4? Like your idea is very good. Try to focus rather than 3-element sets, go to 2-element sets. Try to focus on smaller size of sets. That may possibly give you some information, and then you can actually do this for your idea. You're doing it for 3 sets, right? F of 1, F of 3, and F of k. Or F of 2, F of 3, and F of k, right? Can you do it for 2 element sets?
Yes.
How?
1 comma k.
No. Okay. So what value of k, right?
It cannot be equal to 2.
So you have that if 1 comma k is not sum free, then f of k comma f of 1 is not sum free. That is, f of k should not be equal to twice of f of 1 or f of 1 by 2, right? Try to use this. Try to first construct an image set which is not sum free, and then go back to the original set. Yes, perfect. So like the chat messages. So the set x comma 2x is not sum free, just because you could choose this not x plus x is equal to 2x, right? And in our original problem, we had not necessarily distinct x by z. X and y may be equal. So can we do this for the image set? That is, for some a, we choose a b such that f of b is twice of f of a. Just because surjectivity, we can do this. There's a set f of a comma f of b. This is not sum free, right? Just because this set is like f of a comma twice of f of a, which is not sum free. Is this part clear? Hello.
Yes.
Yes. So yes, P is equal. So thus the image set must also not be sorry. The original set also must not be sum free. That is, a comma b must not be sum free. So like what you're saying, Pranav, is that b equal to 2a, or it also can be a by 2. Do you get this? Yeah. So you want b equal to 2a, right? Just because you want to prove f of x is equal to x works. So you want b equal to 2a, just because of the reason. This means f of x and x should have the same parity. Why so? Why should f of x and x have the same parity?
Because like for any even x, then for any k that is not equal to 2x, k cannot be equal to 2f of x or f of x by 2. But for all k that are not equal to 2x or x by 2. But something has to equal to these two values. So if f of x is not sorry, like what I meant to say is that if x is odd, then f of x must also be odd.
1 second. Like you say that f of x and x is same parity, right?
Yes, like I forgot to take the even case, but for odd case it works.
Second. So if f of odd is even, then you want to choose b to be odd, right? B to be that odd thing. And then you can choose a suitable a.
No, like so
And
a
then
comma
choose
b is not sum free, and
yes.
a is odd. So b cannot be equal for any b that is not equal to 2a. Then f of a sorry f of b will not be equal to 2f of a or f of a by 2. But something will but f of something will have to be equal to f of a
Yeah,
and f of a by 2. But
Yes.
there is only one value that can take both of these values.
So you're saying that for odd a, you have f of twice 2a is equal to 2 times f of a, right? Is this
Yes.
true for odd a? Odd a. Good. So let's do this higher powers. Like let's do this for even a. So if A is equal to okay, there's a big chat message. If we replace A with A by 2, yes. So yes, the chat is actually saying that perfect. So okay. So we have that if f of A by 2 were A, twice of f of A, that is if B were A by 2, then we can do this operation again. That is called this thing to be 2n. Then we can actually choose another, let's say C, which is equal to 4n. That is twice of f of A by 2. Now, just as the previous thing, just like what we did previously, we have that the set f of C and f of A by 2 is not sum free. That is f of C and f of A by 2 is not sum free. Thus, its original set also must not be sum free. That is C and A by 2 must also not be sum free. But this means that C is either twice of A by 2, which is A, or C is A by 2 by 2, which is A by 4. Can C be A? Yes, why not? Oh, you don't have injectivity yet. We do not have that f is 1, 1. We have that f is surjective. So why can't C be A? Can C be A? How did we construct C? What was F? Yes, perfect. So if C were A, but we constructed C to be like f of C is equal to 4n, right? But we assume that f of A is equal to n. So how can C be? Yes, exactly. So C is not A. This is not possible. So C must be A by 4. That is f of A by 4 is equal to 4n. But then we can do this again. That is, we can actually go to f of A by 8 to be equal to 8n and so on. But this cannot continue indefinitely, right? Just because like you first said that for odd A, we'll just stop at A by 2. So if A is equal to twice of some odd number, twice times an odd number, we will stop at A by 4 too, right?
Yep.
And if A were like 4 times an odd number, we will stop at 4n and so on. So this process can't go indefinitely, right? Is this part clear? Yes. Like, is this part clear to everybody? Okay, sure. So our original assumption was wrong. That is, f of A by 2 is equal to twice of f of A is not true. Because we just assumed this and continued this procedure again to get a contradiction. Thus, we must have that B were 2A. B should not be A by 2, and thus it must be 2A. That is, we have that f of 2A is equal to twice of f of. Yes, very useful. Awesome. Now let's go back to the idea that we started with. See, we're here, right? So we started with this, right? We took a k, which is equal to f of 1 plus f of 3. Then they said f of 1, f of 3, and f of k is not sum free. Just because of our construction of k. Thus, its original set must also be not sum free. That is 1, 3, and k must not be sum free, as said by Arav. Thus, k must be 2 times 1, 2 times 3, 3 plus 1, or 3 minus 1. So 3 minus 1 is 2 again. So k must be 2, 6, or 4. So what if k were 2? So if k were 2, then we actually have that f of 1 plus f of 3 is equal to f of 2. But we just prove f of 2 is equal to twice of f of 1. Just because we actually have f of 2a is equal to twice of f of a. Right? So now we have that f of 3 is equal to f of 1. Now what should we do? Like, is this part till now everything is clear, right? Hello. Is it clear to everybody?
Can you just repeat in short?
Yes, I will repeat in short, sure. So first we restricted the problem to be if the image set is not sum free, then the original set is not sum free. Like if f of small a where a is in capital A is not sum free, if there existed a set capital A, then the original set capital A is also not sum free. Just because if this, like if capital A were sum free, then by problem statement, we must have that the image set is also not sum free, right? Hello. Is this clear?
Yes.
Yes. So then we try to choose good non-sum free sets so that we could have some information with them. So the smallest non-sum free set that we could think about was x and 2x. So to choose it to be an image set, for sum a, we choose a b such that f of b is twice of f of a. We can do this by surjectivity. Okay.
Yes.
So we must have that our original set, that is a comma b, is also not sum free. Thus b must be either 2a or it must be a by 2. But f of a by 2 is equal to twice. So if b were a by 2, so we'll first take a case that if b is equal to a by 2, then we have that f of a by 2 is twice of f of a as our above assumption. Right?
Yes.
Now we let f of a equal to n. So we have f of a by 2 is equal to twice of n. Now we repeat the exact same procedure again. That is, find a c which is equal to twice of f of a by 2. Like f of c is equal to twice of f of a by 2, which is 4n. Thus the set f of c and f of a by 2 is not sum free. Hence our original set, which is c and a by 2, must not be sum free. Thus c is either equal to twice of a or is equal to a by 2 by 2. So c is either equal to a or c is equal to a by 4. So if c is equal to a, you must have that f of a is equal to 4n, but f of a were n, which is not possible. Thus you must have c is equal to a by 4. But then f of a by 4 is equal to 4n, and then we can repeat this procedure again. So we get f of 8 is equal, f of a by 8 is equal to 8 by 8n, and so on. Right?
Yes.
But this cannot continue indefinitely, right? It must stop at some point. Just because we're working in integers. Just because we're working in integers, right? Like try the example of, let's say 48. You have that assume for f of 48, 1 second, twice of f of 48 is f of 48 by 2, which is equal to f of 24. But then we prove that f of 48 by 4, well, is 2n. We prove that f of 48 by 4 is equal to 4n, but this is equal to f of 12. And then we prove that f of 48 by 8, like we can do this again, is equal to 8n. But this is equal to f of 6 is equal to 8n. Then we can again divide by 2, that is f of 48 by 16 is equal to 16n. But then f of 3 is equal to 16n. But now can we divide by 2? That is this s of 48 by 32, an integer.
No.
So we cannot go after this, right?
Yes.
But we prove that this is our only choice to go down. We have to have f of like something contradiction, right? This cannot be true. We prove that this has to go down, but 3 is odd. So this cannot go down, right?
Yes.
So this is not possible. So what went wrong? The original assumption was f of a by 2 is equal to twice of f of a. This must not be true, right?
Yes.
Thus we must have that b must be 2a only. That f of 2a is equal to twice of f of.
Okay, understand.
Now we were just continuing the starting ideas suggested by RF, that we first choose a k which is equal to f of 1 plus f of 3. So as I said, f of 1, f of 3, and f of k is not sum free. Hence I said 1, 3, and k is also not sum. So k must be either 2, 6, or 4. So I mean this is equal to twice of 1, twice of 3, 3 plus 1, or 3 minus 1, which is again counted. So if k is 2, what happens? We know that f of 1 plus f of 3 is equal to f of 2, which is equal to twice of f of 1. Thus, you must get that f of 3 is equal to f of 1. Now, we have that this is equal to f of 2 by 2. Right? Hello. Hello. Yes. Perfect. So we must have that f of 2 is equal to twice of f of 3. Thus the set f of 2 and f of 3 is also not sum free. Hence the set 2, 3 was not sum free. Which is not true, right? Is this clear that this is a contradiction?
Yes.
Perfect. So like this kind of motivates us to do injectivity, just because we just didn't use much about 3 and 1. Also, injectivity is just that if f of a is equal to f of b, then we must have a equal to b. So let's try to prove injectivity. So let's just mimic the proof that we just did. Can you repeat one more time? Which part?
Just the last part about 1 and 3.
Yes, sure. So we first choose a case such that f of k is equal to, yeah. So if k were 2, we have that f of 1 plus f of 3 is equal to f of 2. But we prove that f of 2 times 1 is equal to twice of f of 1 by this above thing. So we must have that f of 3 is equal to f of 1, right? Is this part clear? Is this part clear?
Yes.
Like somebody else must, right? Vinayak. Okay, so we must have that f of 3 like is equal to f of 1. So we must have that f of 3 is equal to f of 1. But we have that f of 1 is also equal to f of 2 by 2. So f of 2 is equal to twice of f of 3. But then the set f of 2 and f of 3 is not sum free. So the set 2, 3 must be not sum, which is clearly not possible, right?
I understand.
Yeah. Okay. Now this kind of motivated us to prove injectivity, just because we didn't use much about 3 and 1. So like injectivity is f of a is equal to f of b for some ab, then a must be. So let's think about this. So if we have for some 2ab, f of a is equal to f of b, then just repeating what we did just now, this is equal to f of 2b by 2, just because of this. Thus f of a twice of f of a is equal to f of 2b. So the set f of a and f of 2b is not sum free. Hence our original set, which is a, 2b, must also not be sum. So a is either equal to twice of 2b, which is 4b, or is equal to 2b by 2, which is just b. But let's just assume for now that a is not equal to b. For the sake of contradiction, let's assume f is not injective. So we don't have this. So a must be 4b. So let's go back. That is f of 4b is equal to f of b, which is also f of 2b by 2. Thus, we have that f of 4b is equal to f of 2b by 2. But f of 4b, which is equal to f of twice of 2b, second, is equal to twice of f of 2b, right? As above. We proved this. But then these two are not equal. Positive integers. So this is not possible. This f must be injective. Is this part clear? Perfect. So we have s is injective. Awesome. So we originally had f was surjective, and now we have this injective. Brilliant. So let's go back to our original idea like that. What we were doing here. I'll just get this idea down 1 second. So f is bijective, exactly. So what we were doing, we first use a k, which is equal to f of 1 plus f of 3. Then the set f of k, f of 1 and f of 3 is not sum free. So k, 1, k must not be sum free. Hence k must be equal to 2, 6, or 4 as above. We prove 2 cannot be true. Now let's think about 6. So we have f of 6 to be equal to f of 1 plus f of 3. But f of 6 is equal to twice of f of 3. So again, we have f of 3 is equal to f of 1, which is not possible because of injective. So again, neither can 2 hold true, neither can 6 hold. So k must be 4, which is essentially what we wanted to prove. So we have f of 4 is equal to f of 1 plus f of 3. Is this part clear? Is this part clear, like how we rejected 6 also? That k also cannot be 6. Okay, perfect. So good. Now let f of 1 equal to c. Let it be c for some reason. We have that this is equal to c plus f of 3. Now what is f of 4? Sorry. F of 4, this is equal to twice of f of 2, which is equal to twice of f of 1, which is equal to 4c. Thus 4c must be equal to c plus f of 3. Hence f of 3 must be 3c. So we have f of 1 is equal to c. F of 2 is equal to twice of f of 1, which is 2c. We just prove f of 3 is equal to 3c. And we got that f of 4 is equal to 4c2. Right? Hello.
Yeah, I can get it.
Yeah. So can we generalize this? That's can we prove f of n is equal to nc? So like just because we've done the base cases, we'll try proving with induction. That is, assume f of k is equal to kc for all k at most n. And let's prove it for n plus 1. Let's make the exact same proof that we've been doing till now. That is, we choose some x, which is equal to f of 1 plus f of n. The same thing we did for 3, right? We'll do it for n similarly. So we have the set f of x, f of 1, and f of n is not sum free. Hence, the original set x, 1, and n is also not sum free. I know that n is at least 4, so n cannot be 2 times 1. So we must have that x is either equal to 2 times 1, which is 2, 2 times n, which is 2n, n minus 1, or n plus 1. We want x to be n plus 1, right? Just because we want f of n plus 1 is equal to n plus 1 times c. Hopefully. So can x be 2?
No.
Yeah, because of injectivity. So if f of 2 is equal to f of 1 plus f of n, just because this is equal to twice of f of 1, we have that f of 1 is equal to f of n, which contradicts injectivity. So we ruled out 2, and similarly we can rule out n, just because f of 2n is equal to twice of f of n. So now we are left with n minus 1 or n plus 1. So if x were n minus 1. So if f of n minus 1 is equal to f of 1 plus f of n, can this be true? Can this be true? Yeah, perfect. Just because of inductive hypothesis, we have that f of n minus 1 times f of n minus 1 is n minus 1 times c, right? Just because we assumed f of k is equal to kc for all k at most n. And we have that this is equal to c plus nc, equal to n plus 1 times c, which is clearly a contradiction. Thus, we must have that k is equal to n plus x is equal to n plus 1, and hence f of n plus 1 is equal to f of 1 plus f of n, which is equal to n plus 1 times c. Yay. So we've completed our induction, and we have that f of n is equal to nc for all. And due to surjectivity, as stated in the starting of the problem, we must have that f of 1 n is equal to n for all. This completes our proof. Is the proof clear? Are there any questions with the proof? No questions. Awesome. Perfect. Let's do another problem. Can you say the last part once? The last part, the induction step. Okay, I'll just repeat after induction. So we first assume, just because, like, look, the base case as we did it. We proved f of 1 is equal to c. We proved f of 2 is equal to 2c. Proved f of 3 is equal to 3c. And f of 4 is equal to 4c. So we want to prove f of n is equal to nc. So we have done the base case of induction, and we assume that f of k is equal to kc for all k at most n. So just like we've been doing previously, just because of surjectivity, we can choose an x which is equal to f of 1 plus f of n. So the set f of x, f of 1, and f of n is not something. So the original set, which is x, 1, and n, must also not be something. I was telling how you took c equal to, okay, just that part. Because surjectivity. Just because you get f of n is equal to nc, f is surjective, right? Surjective means f takes every values. That is for all positive integers m. There exists k, let's say, such that f of m k is equal to m. So just take 1. Oh yes, okay, perfect. So are there any questions to anybody with this proof? No questions? Okay, perfect. Perfect. This one. Pretty cool. Okay. Oh, okay. Is the problem visible? Like, so this is the next problem. We need to find all functions g from n to n such that g of m plus n times g of n plus m is a perfect square. So again, take 5 minutes to think about this. If you don't know.
A number of the form gx equal to x plus t works.
Yeah, perfect. So first guess is there. G of x is equal to x plus d works. Perfect. Okay. So yeah, I forgot to put guess. So that's your guess. This works. So we need to prove it. Let's take 5 minutes to think about this. Go ahead. Or were you saying something? Okay, just something. Were you saying something? Any ideas?
Gm plus n must equal to gn plus m, as in any other case where doesn't work may not always hold for all m and n in natural numbers.
One second. I just want to wait a minute. Why? Like this just finishes the problem. Like this is the main stuff you have to do. Right? How do you claim this?
Like for all like say for some function for all m comma n, it may not always be the case that the product will always be like a perfect say this. If this statement doesn't hold to gm plus n is not gn plus n, for every m comma n, they may not always become a perfect square.
That's why? Which M and N would give a contradiction? Why should it not? Bit more
For-
rigorous, right?
Like if you have a case where like n equal to 0, actually no, that will not hold. Yeah, sorry.
M and N are naturals. So we cannot put 0 in.
Yeah.
Like in the chat. I guess in the chat message actually uses 0. Sorry, G of 1. So there is a chat message saying that G of p minus G of 1 plus 1 is an odd power of a prime, right? And why should this be true? Let's see. Whether this times, okay, I get it. Perfect. Yeah, this is true. So that odd power can be literally anything. So you actually have that p divides this, right? So can you generalize this? This is a very good idea. Like, just try to generalize this. Okay, so like I'll just give a hint. This actually try to think more FE like. Like when you're doing an FE, rather than plugging values, what else do you try to prove? Hello, I'm audible, right? Hello. Hello. Yes, exactly. Injectivity or surjectivity. What do you expect? First of all, you have that G is equal to X plus D. So surjectivity, like, don't waste your time proving surjectivity, right? Can we prove by taking G of X to be as a polynomial? Like G is a function, so you cannot take it to be a polynomial. Like G is a function, so you cannot take it to be a polynomial. But yes, the idea of injectivity or surjectivity is very nice. Like we can't prove surjectivity because general G is not even surjective. So let's try proving injectivity. So if for some A and B, you have that G of A is equal to G of B. How do we continue? Okay, go ahead.
Sorry. G of A equals to G of B. Can you plug in M and N is both A and B?
In the original thing, so let's like call this assertion to be P of, so you want to do P of A comma B. With P of M comma N as assertion, right?
Right. But
yes, call this thing C.
It will give us a perfect square already.
This is a perfect square.
So, but if this is injective, the function is injective, so only hold if A equal to B.
No, like we need to prove function is injective. We are now proving function is injective. So we assume this. And now we want to prove A is equal to B. And so Akash, what do you mean to prove that if it generalizes if we put 1 is n? Okay, I guess you're trying to tell about this thing, right? Yes, I get it. Okay. Oh my God, what's something? Right. I'll come to that in a moment. First, try to prove injectivity. I'll come to what I was saying in a moment. First, try to prove injectivity. So assume g of A is equal to g of B is equal to C. What do you do while proving injectivity? What is like the steps you should do? Like, what is the first thing that you want to prove some F is surjective?
If
But-
C plus A into C plus B will also be a perfect square if A equal to B. In any case, otherwise,
This is also a perfect square, right?
Yeah.
This is 4 times 9.
what if like C plus A and C plus B are already perfect squares?
Like you just take A to be 3 and B to
Yeah.
be 8. Then f of 3 and f of 8, assume it to be 1. So like this is to be a perfect square. 1 plus
Yeah.
3 times 1 plus 8 is 4 times 9, which is 36, a perfect square. So this can be true for A not equal to B. But you have more information. Like whenever you're proving something, you do this, right? You take these two assertions and try to subtract or get some stuff with it. So we have that g of A plus n times g of n plus A is a perfect square. This is a perfect square. And g of B plus n and times g of n plus B is a perfect square. Right? Is this clear? I'm audible, right? Yes, it's perfect. Now none of that. None g of A is g of B, so write this thing to be C. God. Delete this. What? One second, sorry. So we have that C plus n and into g of n plus A is a perfect square. And we also have that C plus n times g of n plus B is also perfect square. Now note that n plus C can literally be anything. So you can choose any good n, like what you did in the starting. Just choose it to be something very nice like P minus g of 1. Right? Just mimic this proof. That is just to choose n to be P minus C for large enough P. You have that P times g of P minus C plus A is a perfect square. Thus, this must be an odd power of P or equivalently P divides G times P minus C plus A. Now this is also P, and similarly P also divides G times P minus C plus B. P divides both of these numbers, it must divide the difference. Thus P divides A minus B. But as we could make P to be any arbitrarily large number, we must have that this whole quantity must be equal to 0. Hence A is equal to B. Is this proof clear? And also this is what I was trying to refer to generalize. We try to make, like you did for G of 1, right? Do it for 2 different values and then do it. This is like what Akash was doing, trying to generalize this. This is what I was trying to emphasize, like what is trying to tell you. Is this proof clear of injectivity? Can you please repeat once? Of course. So we want to prove G is injective. So assume G of A is equal to G of B is equal to some C. Then we consider P of A comma N, like P of M comma N is the original assertion. That is, in this we put M equal to A. So we have that, note that G of A is equal to C. So we have that C plus N times G of N plus A is a perfect square, and C plus N, because G of B is also C, times G of N plus B is a perfect square. Is this part clear?
Yes.
Okay. Now we choose N to be a P minus C, where P is a very large prime. Thus P times G of P minus C plus A is a perfect square. Hence P must divide this thing, right?
Yes.
Thus P divides G times G of P minus C plus A. Similarly, P must also divide G of P minus C plus B. Right? But just because of the other assertion, because both of these numbers are same, which are the prime P. Clear? Okay, I'll repeat once.
Yes.
Okay. So P must divide their difference. Thus P divides A minus P. But we can choose P very large, such that a very large number dividing some smaller number, the smaller number must be 0. Thus A must be P. You get it?
Yes.
Perfect. So we proved injectivity. Very good. Now comes our main step. So can we generalize injectivity? That is, what special thing do we use about C? Try to do it for general A and B. And of course, we won't get A equal to B, but can we get some condition? Like just P divides A minus B is also very useful. That is what I'm trying to say. We're just focusing on divisibility by P, right? In this whole part, rather than focusing they're perfectly equal, we just focus they're perfectly equal mod P, right? Hello. Yes. So of course we can't pick P to be arbitrarily large, but we'll choose P suitable such that G of A and G of P are the same mod P. If there existed a prime P, then we can literally mimic this proof again, right? So I'll just do this. So let's try to do this again, like what we were trying to do without G of A equal to G of P this time. Here G of A plus N times G of N plus A is a perfect square. We also have G of B plus N times G of N plus B is a perfect square for some A and B. Now, like we did above, we can choose A equal to B and prove G of A is equal to G of B modulo B. Very good. So you want to prove that if P divides A minus B, this implies P divides G of A minus G of B. How? Can you just explain this?
Actually, like it was just an idea.
Okay, very good. This idea is all very good. Try to do the reverse of it. Like try to prove if P divides G of A minus G of B, this actually implies P divides A minus B. This idea is very good. You can just prove the reverse of it. Why? Why to think about the reverse and why to not think about the straight part? Because try to mimic the proof of injectivity. Again, we just use that this C, that G of A and G of B are same modulo P, right? And 2, we can actually choose a good N. So in this thing, if we fix A and B and we vary N, like we choose a good N, we have more freedom on this factor rather than this factor, right?
Okay, yes, I have an idea of how to prove the reverse of this statement.
Yes, very good.
So like if G of A, if P divides G of A minus B, then we can say that G of A and G of P remain are congruent to A modulo P. Then we can put N as P minus K, and then we can prove that G of P minus K plus A and G of P minus K plus B both have both of them have P as one of their factors. So A should be N should be the same remainder modulo P.
Yes. The proof is perfectly right. The idea is perfectly right. But there's just one tiny thing that can actually have an issue. What is that tiny thing? When you choose N to be P minus K, G of A can sadly be this. Right? This can be G of A. But then G of A plus N turns out to be P squared. So you might not have P dividing G of N plus A. Do you get this?
Yes.
So your idea is perfectly right. Just choose N rather than to be P minus K. Try to choose something different. Try to just put an L right here. It shouldn't make much difference. L is co-prime to P. L is integer. We will choose L co-prime to P. So that LP minus K, we will choose N to be this, right? Okay, wait just 1 second. So So 1 second. First of all, we can choose an L such that G of P LP minus K plus G of A is not divisible by P square, right? Just because we know this is clearly divisible by P as a resumption, we can choose an L such that this is not divisible by P square, right? Is this part clear? Just 1 second, emphasize it. Like for simplicity, I'll just put K to be G of A. Okay. It wouldn't make much of a difference. Like because I can choose L to be sufficiently large enough so that it's positive. So I'll just put K to be G of A. We can actually do it for K itself.
What is P equal to again?
P is a prime dividing G of A minus G of A. Fine, let's just do it for K. So we want that P square, we want P square to not divide LP minus K plus G of A and P square to not divide LP minus K plus G of P, right? Then we can continue your argument and get that P divides A minus P, right? Like we want this, we don't have this. 1 second, I'll just write. We want this. Okay. Is this clear? Hello, I'm audible. Yeah, hopefully. He can hear me, right? Okay. So how do we choose a good L? Like, how do we choose a good L? Because just choosing L would give us what we want to prove. Like
Exactly, L equal to 2 might work if P is an
L
odd
equal
prime.
to P. No, L we need to be co-prime mod
L
P.
equal to 2, I said. L equal to 2.
Okay, L equal to 2. L equal to 2. Perfect. Let's think about this. 2P minus K plus G of A. Why should this work?
Because if P is an odd prime, then what will happen is 2P minus GA is equal to K as well, right? So,
Oh, actually, G of A is congruent to K mod P.
okay, so then this what will happen is then 2P minus K plus GA. Okay, sorry. Is okay, never mind. Sorry, I thought K was equal to GA.
That's okay. So just write G of A minus K to be some, let's say, P times C, just because that's what we assumed, and G of B minus K to be some PD. Right? And we want P square to not divide LP minus PC, or equivalently P to not divide L minus C, and similarly P to not divide L minus D. We can clearly choose an L, right? Is this part clear? Like you can clearly choose an L such that L is not congruent to D or C modulo P,
Yeah.
right?
Uh-huh.
This is clear, right?
Uh-huh.
To everybody. And like if P square, like for 2, this can run into an issue, but just make this a 4. Just make the 2 a 4 and repeat the same argument again. You'll end up with PQ here. And you can actually finish it off. Like even for 2, it will work. That is for every prime, like for any prime P dividing G of A minus G of P. We have that this implies P divides A minus P. Clear? Just because it's repeating the exact same argument again. That is again, we have P divides G of N plus A, P divides G of N plus B, subtracting. Perfect? Clear. Clear to everybody? Yep. So good. Now we just choose A and B to be consecutive. That is, if there existed a prime, if there existed,
Just at last, what we have done?
Yeah, I'll just repeat. We got 1 second. This part, right? We can choose a good L.
Yes, here what you have done after taking G of A minus K is equals to PC, what we have done next?
Yes, I'll explain. So we hopefully wanted that LP minus K plus G of A to have an odd exponent of P. Right? So we just do it for 2 square, like for P square, we will find an L so that P square does not divide LP minus K plus G of A, and P square does not divide LP minus K plus G of A, where we choose N to be LP minus G of K. Okay?
Yes.
Like I'm just doing it for P square, you can generalize it for 2. If this is true for odd primes, you can do it for even 2. It's not hard. The same proof will always work. So we assume that G of A is congruent to G of B is congruent to K mod P. So let G of A minus K equal to PC and G of B minus K equal to PD. Okay?
Yes, here it is clear. After what we have done next?
After that, we want that P square to not divide LP minus PC.
Yes.
This is equivalent to P to not divide L minus C.
Yeah.
And similarly for the other, this is equivalent to P to not divide L minus D. Right?
Yes.
So we can clearly choose a good L.
Yeah.
Get this?
Yeah, yeah. Okay, now.
Perfect. Now I'll just, for completeness, I'll do it. So we actually have P dividing G of n plus A and P dividing G of n plus B. In. Thus the difference subtracting, we actually get whenever P divides G of A minus G of B, we have P divides A minus B. Now we choose just A and B to be consecutive. So if there was a prime dividing G of A plus 1 minus G of A, we have that P divides A plus 1 minus 1, which is 1. Sorry, A plus 1 minus A, which is 1, which is clearly not possible. Thus, we have G of A plus 1, not exactly. G of A plus 1 minus G of A is equal to plus or minus 1. This does not exactly form an arithmetic progression, just because we can actually go minus 1s. We get this?
Yes.
Yes, so let G of 1 equal to C. So what we're actually doing from going to consecutive integers, like 4, 5, 6, 8, 9. Like whenever you're going from G of A plus 1 to G of A, sorry, we're going from G of A to G of A plus 1. That is whenever we're computing G of A plus 1, we're actually adding plus 1 to G of A or minus 1 to G of A, right? So if G of 1 starts with C, and then like the sequence is just like plus 1, or sometimes minus 1, and plus 1, minus 1, minus 1, plus 1, and a minus 1, right? So from from the previous value, we're just adding 1 or we're adding minus 1. Okay? Clear? Or are there any questions? Yeah.
Yes.
So can there be both 1s and minus 1s? So let's observe what happens right here. So from G of 2 turns out to be C plus 1. G of 3 turns out to be C plus 2, like plus 1 to G of 2. And G of 4 goes minus 1, so we go to C plus 1. And then we go to C plus 2, C plus 1, C, C plus 1, C. But note that G of 2 is equal to G of 4, right? But G was injective, exactly. So can we have both 1s and minus 1? So what actually happened out here, we started at n plus 1, and n plus 2. If there was a plus 1 right here and a minus 1 right here, and then G of n something, then we actually went to G of n plus 1, and then to G of n. But this contradicts injectivity. Thus, in this sequence of plus 1s and minus 1s, we cannot have both plus 1 and a minus 1. Like you can just repeat the same proof with minus 1 and plus 1. Clear? So in this sequence of plus 1s and minus 1s, if we had both a plus 1 and a minus 1, we would either have two consecutive indices with the plus 1 and a minus 1, which is contradiction into injectivity, or a minus 1 and a plus 1, which is similarly contradicting injectivity. Is this clear? Yes, is this clear to everybody?
Yes.
So either we're going all plus 1s or we're going all minus 1s. Thus, we're either going C plus 1, plus 1, plus 1, and so on. That is G of n is equal to n minus 1 plus C, or is equal to n plus D, where D is non-negative, which is exactly what we wanted to prove. Or we're going minus 1, that's C minus 1, minus 1, minus 1. But then we have the G of n is equal to C minus of n minus 1. But then for large n, this is negative. But we were working from natural numbers to natural numbers, so this case is not possible. Thus, we have only our one case, and this is our only solution. Is the proof clear? Are there any questions with the proof? Clear. Perfect. So this idea of injectivity and that injectivity over mod P, or that very good idea by Arav, this one, these are quite useful. Even though we didn't have any equality in our original problem, we could still prove injectivity. And injectivity over mod P, or this is like injectivity over mod P. These are very quite useful ideas, and we can actually use them whenever you don't even have an equality. Like we had just a perfect square, and we actually could prove injectivity and injectivity over mod P. So these are quite useful ideas. So like another problem where you can actually use this idea is just 2007 and 5. I will not do it right here because of time. Like I'll just end. This problem exactly uses the same ideas as this proof. It's literally the same ideas. Even though the problem statement is very different, but the problem uses exactly the same ideas. So if you want to try, you can try this problem. That's it from my side. Hope you enjoyed. I hope you're convinced that these nice looking NTFEs are quite good and fun to solve. Hope you enjoyed. Thanks for attending. That's it from my side. Can we get some homework problems? Yes, sure. So I'll just, one is 2007 and 5. This one, this is actually 2007 and 5. You can see the problem, right? This problem uses exactly the same ideas as the previous problem, even though the statement is very different. What do you mean to say, Akash? I didn't like, what do you mean to say? It's visible. Okay, okay. Perfect. And like NTFEs, you can just find them anywhere. You can also try this problem. This problem is not that, it's good. Like it's nice. You can see the other problem, right? This too many F's. You can see it, right?
Yes.
Yeah. So F to the K of N is just F applied K times. And this is like quite easy in compared to the previous two problems. But I would like recommend trying this problem. This is quite good. But it's quite similar to the previous problem. Hope you like, that's it from my side.
Thanks for the class. I'll stop recording.
Yes, sure.